welcome in this new video. In this video, I will explain the equality of a second order derivative of a function. First, we consider the equality at a particular point, and then we generalize or we prove a theorem regarding the equality of second order derivative of a function. Derivative of a function f of a comma b, and we consider the derivative uh, with respective to y first and then with respective to x. So this is the derivative del by del x of delta by del x of the derivative of f with respective to y, a comma b, f suffix y. Okay, so by definition this is a limit h tends to 0 f y at a plus h comma b minus f y at a comma b divided by k. Suppose this is a equation number 1. Then fy at point a plus h comma b equal to, by definition this is the derivative with respect to y, so limit k tends to 0 point a plus h comma b plus k minus f of a plus h comma b divided by k, and the fy at a comma b equal to derivative, by definition this is limit k tends to 0 f of a comma b plus k minus f of a comma b divided by k. So let us put this value in this equation. F x y at a comma b equal to limit h tends to 0, limit h tends to 0. Here is mistake, friend, we are this differentiating with respect to h, so here there must be h, so 1 divided by h into fy at a is equal to, this is a limit k tends to 0 f of a plus h comma b plus k minus f of a plus h comma b divided by k minus limit k tends to 0 f of a comma b plus k minus f of a comma b divided by k. Okay, so we get this derivative, this expansion. Now limit common, limit we write it as h tends to 0, k tends to 0, and this is 1 divided by h into k, denominator is same, so there is a addition subtraction of numerator, a plus h comma b plus k minus f of a plus h comma b minus f of a comma b plus k minus f of a minus minus plus f of a comma b. So this much value we get f of derivative of f with respect to x y. I will write here the value so that we can compare the another value of this function, then substituting this value here, so we have this value is equal to, now limit h tends to 0, k tends to 0, 1 divided by hk into f of a plus h comma b plus k minus f of a plus h comma b minus f of a comma b plus k plus f of a comma b. So this is our value with respect to x y. Now consider another part with respect to yx, means with respect to x first. Okay, Now derivative yx at a comma b, this means this is a del by del y of fx at a comma b equal to limit k tends to 0 fx at a comma b plus k minus fx at a comma b divided by k. Now in this expression fx at a comma at the point b plus k equal to derivative with respect to x means limit h tends to 0 f of a plus h b plus k constant minus f of a comma b plus k divided by h, and f x at a comma b equal to limit h tends to 0 f of a plus h comma b minus f of a comma b divided by h. Let us put this value here in this expression. So f y x at a comma b equal to limit k tends to 0 1 divided by k into fx, that is a limit h tends to 0 f of a plus h comma b plus k minus f of a comma b plus k divided by h minus limit h tends to 0 f of a plus h comma b minus f of a comma b divided by h. So limit and h common, limit h tends to 0 k tends to 0 1 divided by hk into f of a plus h comma b plus k minus f of a comma b plus k minus f of a plus h comma b minus plus f of a comma b. So this is the value of f y x at a comma b. Okay, so here you can see that the right hand side of these two expression is the same, and therefore left hand side of these two expression is also same. So here what we have done here, we have differentiated this function first with respect to x and then y, whereas in this case we have differentiated this first with respect to y and then with respect to x, but in both the case we get the same value of the function. So this is about the derivative of the function, second order derivative of the function with respect to x and y, and we have seen that these two values are equal. Now what about the general case? This is at a particular point a comma b, but what if we consider instead of a as a x and instead of y as a instead of b as a y? Okay, so first we consider the function phi h comma k equal to f of x plus h comma y plus k minus f of x comma y plus k minus f of y comma x plus f of x plus h minus f of x plus h comma, here we write it as f of x plus h comma y and plus f of x comma y. Suppose this is my function, let us call it as a equation number 1. Now consider the function psi of x. This is a function of x, and we consider this function as x comma y plus k minus f of x comma y minus f of x comma y. Then psi of x plus h equal to f of x plus h comma y plus k minus f of x plus h comma y. Then psi of x plus h minus psi of x equal to f of x plus h comma y plus k y plus k minus f of x plus h comma y minus f of x comma y plus k minus plus f of x comma y. So all the terms x plus h here, f of x comma y plus k, and this is nothing but phi of h comma k. So here we get phi of h comma k equal to phi of h comma k equal to psi of x plus h minus psi of x. So applying the mean value theorem over the interval x comma x plus h for the function psi, we have psi of x plus h minus psi of x divided by h equal to psi dash at x plus theta 1 h. Hence this value phi of h comma k equal to h into psi dash of x plus theta 1 h. But what is a psi dash? Psi of x is equal to this one. So psi dash of x equal to derivative with respect to x, fx at x comma y plus k minus fx at x comma y, and then at the point x, psi dash at x plus theta 1 h equal to fx at x plus theta 1 h comma y plus k minus fx at x plus theta 1 h comma y. Let us put this value here. So phi of h comma k equal to h into fx at x plus theta 1 h comma y plus k minus fx at x plus theta 1 h comma y. So this is the function fx where the interval is y comma y plus k, and for this interval if we apply the Lagrange's mean value theorem, we have fx at x plus theta 1 h comma y plus theta, here you can see that fx at y plus k minus fx at x plus theta 1 h comma y divided by k equal to f yx at x plus theta 1 h comma y plus theta 2 k. So this term is nothing but by Lagrange's mean value theorem is equal to h into k into f yx at x plus theta 1 h comma y plus theta 2 k. So we have by Lagrange's mean value theorem we get this value, that is from the last expression we have the value of the phi of h comma k is now this will be phi of h comma k divided by hk equal to fyx at x comma theta 1 h y plus theta 2 k. Now consider the function capital F of y equal to f of x plus h comma y minus f of x comma y. If we consider this function, then capital F of y plus k equal to f of x plus h comma y plus k minus f of x comma y plus k. Then f of y plus k minus f of y, if we calculate this, we have f of x plus h comma y plus k minus f of x comma y plus k minus f of x plus h comma y minus plus f of x comma y. We have this value. Again this is nothing but phi of h comma k. So we now get phi of h comma k is nothing but the difference of this function capital F, that is phi of h comma k equal to capital F of y plus k minus capital F of y. So capital F is a function defined over the interval y comma y plus k, and over this interval capital F of y plus k minus capital F of y divided by k equal to capital F dash of y plus theta 3k. So therefore this phi of h comma k is nothing but this is a k into capital F dash of y plus theta 3k by the definition of Lagrange's mean value theorem. But what is a capital F of y? Derivative of capital F of y is nothing but f dash of y equal to derivative fy of x plus h comma y minus fy of x comma y. Okay, so let us put this value here. Then capital F dash of y plus theta 3k equal to fy of x plus h comma y plus theta 3k minus fy of x comma y plus theta 3k. We put this value here, so we get k into fy of x plus h comma y plus theta 3k minus fy of x comma y plus theta 3k. Now friend, this is a constant term and it is a derivative. Again we apply fy. This is my function and the interval is x comma x plus h. For this function we apply the Lagrange's mean value theorem, and we get, this is with respect to x, so we get k into h into f x y at x plus theta 4 h comma y plus theta 3k. Okay, so from this expression we have now the value of phi of h comma k. Phi of h comma k equal to phi of h comma k divided by hk equal to f x y at x plus theta 4h comma y plus theta 3k. Left hand side is equal, so right hand side must be equal. That means fyx at x plus theta 1h divided by y plus theta 2k equal to fxy at x plus theta 4h comma y plus theta 3k. So as h tends to 0, k tends to 0, if we take this value equal to 0, then you observe that we get the required result. That means the value derivative of f with respect to x and then y at x comma y is nothing but equal to derivative of f with respect to y first and then with respect to x x comma y. So we get this. So whenever this function f of x comma y possesses a second order derivative, second order derivative, then f x y x x comma y equal to f x y x comma y. So this is about this equality of the derivative of a function. Thank you friend, thank you for watching a video.